You may have noticed fisheries observers measuring fish and cutting into their heads and wondered what the hell they're up to. This process is like opening a window into a fish's life. In this section, we'll be looking at the process of measuring and aging fish and estimating growth rates with the aim of building an understanding of the size and age structure of the fish stock. Going back to our diagram, age and growth fit here. We want to understand the size and age structure of the fish stock at any point in time. So why is this important? The answer is that if we know the size structure of the stock, then we can estimate how many new fish are in the population, which ones will get caught, which ones are breeding, and which ones are dying. Have you ever wondered how scientists measure the age of fish? Many people think it's as simple as just looking up the fish's date. Well, as it turns out, looking up a fish's date isn't really that helpful. The process of measuring and aging fish is the first step in the understanding of the size and age structure of the fish stock.
We've got three sizes of flathead. We've got our XL flathead, which is the width of a standard fish bin. Our number one flathead, which are 13 inches or 28 centimetres, I think it is, up to the width of the fish bin. And the small fish, which is the 28 centimetre fish, which is legal size, up to 13 inches, which is, I don't know what it is in metric, I'm too old for that crap, but yeah.
A good way to demonstrate this is looking at the fish unloaded by Wayne at the co-op. Wayne grades the fish for market because he gets a different price for different size fish. Here we see fish bins filled with fish of the same grade, from small to extra large. In a normal shot, Wayne usually gets a few bins of smalls, a few bins of extra large, but mainly bins filled with medium and large. Believe it or not, what we're creating here is a frequency distribution graph, and it's much the same as graphs created by scientists to explain the size structure of a fish catch. Frequency distributions show counts of things in different categories. On this line we have the sizes of the fish caught by Wayne, and on this line we have the numbers of bins of fish caught. If we draw bars over the top of our bins here, this is what scientists call a frequency distribution graph. Scientists use graphs a lot to represent relationships between two different measurements, also known as variables. In this case, the measurements, or variables, are length along the bottom and number of bins along the side. Scientists do basically the same thing as Wayne, except rather than grading the fish into small, medium, large and extra large, they grade them into 1 centimetre size classes. Let's see how scientists obtain a length frequency distribution. The first step is to measure the length of heaps of fish. We'll use tiger flathead. You may well have seen this happening on your boat. It's a common practice. After all this measuring, scientists end up with an understanding of the size range of the fish that get caught in the gear. We can represent these length measurements visually. Our scientist has been very busy and collected a lot of measurements into 1 centimetre categories. Looking closely at these measurements, you can see that the fish are falling into different sizes. Little ones down this end of the scale and the biggest up this end of the scale. As you can see, they're not all big or all small. Instead, what we get is a range of fish lengths which together form the length frequency distribution curve. For some fisheries, length information is all we know about the structure of the population. With most fish, however, we can get age information in addition to length. The advantage of having age information is that we can tell what year the fish were spawned. So, how do you age a fish, and what do ear bones have to do with the process? A fish's ear bone, or otolith, can be aged much the same way as people age trees. If you take a chainsaw to a tree and cut through its trunk, you'll see the stump is made up of rings. Each ring represents 1 year of that tree's life, and by counting the rings you can age the tree. Now, if you take a chainsaw to a fish, then you won't see much at all. So instead, scientists use a knife and then tweezers to pull out the otolith. They embed the otolith in resin, cut it into a thin slice and count the growth rings to get a measurement of age. The problem though with aging fish is that it's expensive and time consuming to collect large numbers. So instead then, scientists age a small number of fish of known lengths and use the length frequency distribution from the stock to estimate ages for the entire population. After aging the fish, the next step is to establish the relationship between length and age. This is known as a von Bertalanffy curve, named after the bloke who developed it. Much easier though is to remember it as a VB curve. Let's have a look at how it works. Here we have our length measurement, and here we have age from youngest to oldest. In the first few years, the fish grow very quickly. As the fish get older though, this growth tapers off to the point where the fish have virtually stopped growing. And here is what the VB curve looks like. What we're representing here is another graph, a bit like the graph we had before of length distributions. In this case though, we have the length of fish on the side and the age of fish along the bottom, youngest to oldest. So here you can see the relationship of length against age. So now we've established what a VB curve is. What's the point of it? In essence, if you know how long a fish is, then you can work out roughly how old it is. In our example here, this fish is 3 years old. Unfortunately though, it isn't quite that simple. The complication is that, like children, fish of the same length aren't necessarily the same age. Or alternatively, fish of the same age aren't necessarily the same length. So how do we deal with this? Well, the next step in the process is to establish the age range of fish at specific lengths. So let's take 37 centimetre tiger flathead to start with. Here are 10 fish at 37 centimetres. We know from their otoliths that they are of the following ages. One of these fish is only 3 years old, 4 are 4 years old, 2 are 5 years old, 2 are 6 years old, and 1 is 7 years old. Now, let's look at this in terms of percentages for the whole tiger flathead stock. At 37 centimetres, 10% of tiger flathead are 3 years old, 40% are 4 years old, 20% are 5 years old, 20% are 6 years old, and 10% of tiger flathead at 37 centimetres are 7 years old. This process is repeated for fish of all lengths to develop what scientists call an age length key. For tiger flathead, the age length key looks something like this. Okay, we're now up to the final step, pulling all this information together so we can understand the age distribution of the whole tiger flathead catch. Firstly, let's turn our length frequency distribution graph into a bar graph. This will help us merge the two together. So, from these two figures, we know how many fish of each length were in the catch and the percentage of fish at each age in each 1 centimetre length category. If we simply merge our table here into the length frequency distribution, we can clearly see that each length has a range of different ages. What we now want is to group all of our ages together and create a distribution that represents ages on the bottom with numbers of fish on the side. This is our final result, the age frequency distribution of the tiger flathead catch. That was a fair bit to take in, so let's have a bit of a recap. Here we have fish of a whole lot of different lengths. From aging of the otoliths, we know that each of these lengths has fish of different ages. By combining these two bits of information, which are length frequency distribution and the age length key, we can see the percentage of fish at each age for each length category. Now, rather than grouping the fish by length, if we group them by age, we get an age frequency distribution.
But there's a bloody lot of flathead going back into the ocean, which we used to catch. And I'm talking 28 centimetre to 35 centimetre fish. Not all of them, but some of them are going back into the ocean, so hopefully the following year or the year after that, those fish will be big enough to catch. I've talked to the guys up the coast and they're saying there's small fish all over the bloody ocean.
I really and truly believe that the last 15 years There's been more flathead than ever, especially on this coast.
So that's about it. To understand age and growth, we've looked at the process for collecting length and age measurements and then converting these to the final outcome, an age frequency distribution. Importantly, a tiger flathead age frequency distribution shows us how many fish for each age are in the catch. If this is done over many years, we can see how the distribution changes over time to better understand key characteristics of the stock, such as strong and weak recruitment events and the effect of fishing on the fish population. In the next section, we'll discover how we can use the age structure of a stock to estimate fish mortality and why an understanding of mortality is so important.